Okay, I'm ready, and I hope that you can see this my presentation clearly. Um, Hello everyone, I'm SK Hong. I'm a professor of Korea University and a dean of Graduate School of Energy and Environment. I'm very honored and also pleased to participate and give a keynote speech in online conference on emerging and enabling materials hosted by Qatar University. Although it is unfortunate that I cannot meet you in person due to COVID-19, I hope, hold on. I hope to entertain you next 40 minutes through this virtual conference by talking about future of seawater desalination with an emphasis on low energy consumption of outer membrane based seawater SWRO desalination. This is the outline of my presentation. I'm going to start with a brief introduction regarding a future of seawater desalination, and then I'm going to talk about SWRO desalination activity in Korea briefly. Then the main topic of my talk today, low energy desalination. The future of desalination technology can be summarized as low energy and thus low carbon, which is integrated with renewable energies such as solar and wind power. Compared to thermal desalination such as MED and MSF, auto-based desalination produce much less CO2 regardless of the source of energy used. Thus, auto has become choice of desalination technology adopted in the current desalination market. However, SWR plants still emit tremendous amount of CO2 to the atmosphere, demanding more technical advancement to further improve energy efficiency. This slide shows a typical SWR desalination process. Raw water is first treated by various pretreatment processes, including DOF, dissolved air flotation, DMF, dual media filter, or UF membrane to remove particles and organics which can cause significant fouling on the membrane surface. The pre-treated fluid is then supplied to the RO system with pressurization by high pressure pump. Lastly, hydraulic pressure in the concentrate is recovered by ERD, energy recovery device. The efficiency of HPP and ERD significantly influence the total energy consumption in SWRO desalination. Some of the SWRO desalination plants in the Arabian Gulf, including the one in Qatar, here are listed in this table. You may notice that the high pressure should be applied due to higher salinity of seawater, and energy-intensive pretreatment process such as DOF is also typically installed and operated. Lastly, second-pass RO such as BWRO is applied to decrease the salinity further. All of these features increase specific energy consumption (SEC) of the SWR plants in the Arabian Gulf. In addition to low energy and carbon, brine valorization is another feature of future seawater desalination. For example, DTRI, Desalination Technology Research Institute of SWCC, Saline Water Conversion Company in Saudi Arabia, has been attempting to develop a series of technology for brine treatment and utilization. Here in this diagram, NF is first installed to separate monovalent and divalent ions. For some reason I cannot use the point here, but that's okay. Then monovalent such as NaCl-rich NF permeate is processed by RO, and further concentrated by high pressure pump here, and diverse new brine concentrators such as apple hybrid process as shown in this diagram. As a result, magnesium and calcium, other transition metals are recovered from NF reject brine, and NaCl, bromine, and other alkali metals such as lithium can be recovered from RO reject brine. We can produce NaOH from highly concentrated NaCl solution, thus adding value to RO brine. Because of the time limit that I have for my presentation, I would like to focus on energy issue mainly today and hope to have another opportunity to discuss more about various technological advancements concerning RO valorizations. The second topic I'd like to talk about an SWR desalination activity in Korea, especially my project, the R&D project in Korea. As introduced at the beginning, Korean government launched a huge SWR desalination R&D project in Korea in 2016. So it's about 4 years ago. Which I was appointed as a director of this research group and center, and we try to achieve 3 technological advancements. Number 1, we try to develop low energy RO system using the world best RO membranes. Number 2, in order to supply very clean water to RO systems, energy conserving algae response pretreatment process is developed. Lastly, low energy future technology for replacing second best RO is being developed, including CDI, which is the topic of Professor Son's presentation in this session. Then we try to develop 1,000 tons per day pilot plant, and then we convert all of those data to the design of 100,000 cubic meter per day real plant, so that we can achieve the 3.3 kilowatt hour per cubic meter of water produced, which is considered to be very low energy desalination energy consumptions. So we are working really hard for this goal of R&D project, and this research group is known as KORE, as shown in this diagram here. In Korea now, SWR desalination, first commercial SWR desalination plant is being constructed in Daesan, which is a large petrochemical industrial complex. And this plant has a size of 100,000 cubic meter per day, with a capital investment of $210 million US. And again, the low carbon and low energy, that is one of the objectives of this plant. And SEC that we are targeting, that is about 3.4 to 3.6 kilowatt hour per cubic meter of water produced. Fortunately, KORE Research Group constructed a pilot plant as shown in this diagram here, and we performed pilot study in Daesan. Hopefully, some of the data that we obtained can be used for construction and operation of this plant in Korea. We also built pilot plant in UAE, and as I mentioned, this is a size of 1,000 cubic meter per day. And this is actual plant. This is not just pilot plant. And we applied all those 3 technological advancements that we have, and we had a ceremony on October 6, 2021, which is like 1 month ago, for the construction and completion of constructions. This is a schematic of the UAE pilot plant, and the Korean University is responsible for coordinating entire process. And then Daewoo, which is number three construction company in Korea, they are in charge of construction of pilot plant. And also seawater, number one water service company in Korea, is responsible for operation of this plant. And Kosong is developing MTBF, which can replace DOF as a pre-treatment. And then Samsung Engineering Company is developing UF membrane process. And then LG Chem, which is known as a company of battery, and they are also making auto membrane, world best auto membrane, and then they provide SWRO and BWRO, which are developed in this project. And then in order to replace BWRO, capacitive deionization technology is developed by C1 Tech in our research group. I'd like to talk about MTF, mesh tube filter, that we are developing. This is an energy-saving algal response pretreatment. MTF exhibits similar algal removal performance with DOF. However, MTF requires only 33 to 39% of the energy needed for DOF. So we can have significant energy saving in these pre-treatment processes. Next, I'd like to introduce advanced SWR membrane, which was developed by LG Chem. As you can see from this diagram, LG Chem developed a series of next generation outer membrane, and including the one which has a flow rate of 9,900 with a salt rejection about 99.88, and that is much better than other membrane on the market right now. So we can say that this is the world best SWR membrane in current market, and actually this one now on the market and being produced in mass quantity. High rate is achieved with the same applied pressure, and the permeate from this outer membrane contains low salt compared to other SWR membrane. This is the simple numbers that we actually applied to design of outer system which containing this outer membrane. As you can see, after this single stage RO, we can produce the TDS level of 160 to 440 millimeter per liter, depending on temperature and the salinity condition. And so we can have significant SCC reduction by adopting this membrane, and then also as a result we can have a smaller BWR system, or we can replace this BWR by CDI technology, which is electrochemical desalting technology. And I would say that this is a lower energy future technology for replacing second phase RO, because with the TDS level less than 2000 ppm, normally CDI has better energy consumption, energy efficiency than BWRO. So CDI can remove salt in the range of brackish RO and consume more energy than BWRO with optimized system or conditions. And so combine all this technological advancement, and we like to demonstrate energy efficiency of all of this the new technology in pilot plant in UAE. Currently, it is in progress. I hope that we can get together at the end of next year. Then I can share the successful story of this pilot plant with you. So now I'm going to talk about the next item, which is low energy desalination technology, and that is the main topic of my talk today. Recently, my research group has published a comprehensive review paper concerning energy issue in desalination in the Journal of Applied Energy. In this paper, the energy consumption of full-scale seawater reverse osmosis plants all over the world were critically reviewed, More specifically, more than 70 data sets for large-sized seawater reverse osmosis plants were collected, examined, and analyzed. Then major technical trends were investigated and identified. Also, critical factors affecting energy consumption of SWRO were analyzed, and future technical direction was suggested to further reduce energy consumption of SWRO plants. This one is now available in the literature. Now, I'm going to talk about overall technical trend, which were deduced from our comprehensive analysis of real-scale SWR plant in the world. Increasing capacity and reducing SEC. The trend of increasing capacity and reducing SEC over the last 4 decades. We can observe construction of many large desalination plants after 2000 years, leading to exponential increase in desalination plant capacity. Over the years, not only the capacity, but also the energy efficiency of SWR plants significantly increased with advancement of ERD, as shown in this diagram. The development of ERD significantly reduced energy consumption of SWRO. The turbine type ERD, FT, and PT is not highly efficient. Thus, to further improve energy efficiency, isobaric ERD such as DVR, or PX pressure exchanger are adopted, as you can see from this diagram. The next, low energy desalination and improved water quality. The next trend identified is the auto configuration for better energy efficiency and water quality. Two-stage RO, treating concentrate of the first stage RO, is designed to increase water quantity. Two-phase RO design, on the other hand, treating permeate of the first stage RO is adopted to increase water quality. As shown in the left diagram in the left, the single stage is more applied in recent years over 2 stages to reduce SEC rather than achieving high recovery. Technical shift from single pass to 2-pass is also achieved to improve higher water quality produced. Now I'm going to talk about critical factors affecting energy consumption from real-scale plant data analysis. Feed salinity and temperature. The effect of feed salinity and temperature, as shown in this diagram, as feed salinity increases, more hydraulic pressure is required to overcome the osmotic pressure of high saline water. Thus, SEC increases with the increased salinity, as shown in the diagram in the left. Furthermore, SEC decreases with the increasing temperature as expected from fundamental theory of outer membrane process. However, no such trend is found in real-scale plant data, since there is a dependence between feed salinity and temperature. For instance, in the Middle East, high salinity is associated with high temperature, resulting in no clear temperature effect on SEC. Plant capacity and pump efficiency. Commonly, if pump size increases, pump efficiency also increases. Our analysis shown in the left diagram presented such a trend. However, it should be noticed that pump size is not always or directly related to plant capacity, since pump is configured to each rack or unit of our brine systems. Thus, no clear trend is identified for the capacity less than 100,000 cubic meter per day. I mentioned the ERD played a key role in reduction of energy consumption. As shown, the efficiency of a turbine is much less than that of isobaric ERD. Thus, in the expansion and retrofit of existing desalination plants have been done by adopting isobaric ERD, resulting in significant reduction in SEC. Lastly, permit quality and auto-pass configuration. It is expected that if the number of pass increases, permit water quality is improved. Single pass configuration typically produces 300 to 500 mg per liter TDS, while 50 to 120 mg per liter of TDS is produced by two-pass system as shown in this diagram. However, more energy is required for the operation of two-pass system, resulting in higher SEC. More specifically, SEC increases with order of single pass, split partial second pass, and partial two pass and full two pass in this diagram. Permit quantity, recovery, and also auto stage. This is the last slide for all critical factors affecting SEC. An increase in feed salinity, as you expected, caused achievable auto recovery to go down. However, if the recovery is enhanced by two-stage configuration, SEC will go up. Therefore, there will be an optimal recovery to minimize SEC. It is between 40 to 50% for single stage, while it is around 60% for the two-stage design. Based on the in-depth analysis of factors affecting SWR energy efficiency, future direction to lower SEC of SWR plants can be suggested as shown in this diagram. First, since high salinity causes SEC to increase, the dilution of feed salinity, such as osmotic dilution by F4, can reduce SEC further. Second, the energy consumed by pumps can be reduced by improving their efficiency and reducing irreversible work, which is not involved in actual separation process. Third, when we try to increase both quantity and quality of desalinated water, SEC will go up. Since outer brine becomes more concentrated, in this case, the logical way to reduce energy use is harvesting osmotic energy of highly concentrated outer brine. So with that, next I'd like to discuss about future perspective based on theoretical SWR energy consumption analysis. Following up our analysis of current energy consumption in SWR desalination plant that I have discussed so far, we performed theoretical analysis and extensive review, and three directions were proposed for improving energy efficiency of the SWR process. Number one, minimize irreversible work of the high pressure pump. Number two, decrease the osmotic pressure of the feed. And number three, recover osmotic energy from reverse osmosis RO concentrate. After the feasibility of each approach was identified by assessing the theoretical minimum energy and the maximum available margin, the strategies for each directions were presented with a technical description and critically evaluated by considering their practical application. This book has been published in the Journal of Membrane Science. Journal of Membrane Science. I think this is available in the literature right now. First, I'd like to talk about the first option to reduce SEC, that is reducing thermodynamic reversibility associated with auto process. The method to reduce irreversibility of high pressure pump used for auto process can be categorized into number one, multi-staging, number two, semi-batch, and batch configurations. as shown in this diagram. The energy supplied to our system is used to separate from the seawater feed, and an additional different type of work is also associated with process that is not directly involved in separation. This work is equivalent to the energy lost by entropy generation, which is known as irreversible work. To minimize the irreversible work, energy should be supplied in a staged manner rather than all at once. For this purpose, stage design have been developed to increase hydraulic pressure gradually. However, the current SWRO desalination plant with multi-stage RO do not show such low energy consumption. This is because the multi-stage configuration is employed mainly for high recovery. To overcome the installation difficulty of infinite multi-stage RO, semi-batch RO, named closed-circuit desalination (CCD), was proposed. The CCD configuration adopts cyclical process where the concentrate is continuously recycled as feed and mixed with fresh feed until the desired recovery can be obtained. Lastly, batch system can minimize irreversible work by gradually increasing the hydraulic pressure as well as reduce the generation of entropy by mixing. Therefore, batch RO would be the most energy efficient process from theoretical point of view. However, the implementation of an ideal batch operation is limited, thus face operational challenge in real-scale systems. This slide shows SEC comparison of multi-stage and batch RO design. In this figure, y-axis represents change in flow exergy of RO design, and x-axis describes the recovery of seawater desalination process. Under ideal condition, batch RO equipped with a variable feed volume consumes the lowest energy close to theoretical minimum energy required for desalination due to minimized irreversibility of batch operation. However, semi-batch RO consumes more energy due to entropy generation, which occurs. The fresh feed is mixed with concentrate. Overall, stage RO design consumes less energy than conventional single-stage RO. From the point of practical application, two-stage RO would be practical solution for minimizing the irreversibility of high-pressure pump. Now, the next improvement strategy, that is decreasing osmotic pressure. If it were possible to reduce the osmotic pressure of the feed, the corresponding hydraulic pressure required to produce a certain amount of water would be reduced, resulting in lower energy consumption. These approaches can be categorized into direct and indirect method, that is, dilution of the feed stream, which is direct, and reducing the relative osmotic pressure difference, which is indirect method. The dilution of feed stream can be also done in two ways. The first is to make recycle stream by using low concentrate water, such as permeate from first pass or concentrate from second pass in the SWR process. The second way is to utilize additional feed stream, such as treated wastewater or brackish water, as shown in this diagram. This is something that we developed in our research group. Single pass SSP RO. To produce pure permeate while maintaining the low energy of single pass RO, we proposed a new RO configuration, so-called split partial second pass SSP. In a PV, the front outer module produces pure permeate, while the rear permeate is more saline. SSP is then designed so the rear permeate is recycled to the feed to dilute. In this way, only front permeate is collected, which is relatively low in salinity, and the rear permeate is mixed with the feed to reduce osmotic pressure of the feed stream. The dilution not only lowers the feed osmotic pressure, but also allows the system to produce low saline permeate from the diluted feed. Thus, purer permeate is obtained without using second pass RO. It is noticeable that SSP consumes less energy than two-pass RO configuration because there is no second pass to operate. In SSP, energy and expense can be saved. As a matter of fact, this technology is patented by our group, and then it is now transferred to industry. So I think that we can see this one in the market pretty soon. The next slide shows FOR hybrid process in which seawater desalination is integrated with wastewater reclamation facility through FOR process for low energy desalination. The first benefit of the FOR hybrid process is a reduction in the thermodynamic energy requirement by simple dilution of seawater with a treated wastewater effluent. In addition, the RO and FOR hybrid system provides the opportunity for wastewater be used with less energy use. In this hybrid process, wastewater is treated by FO process using the osmotic pressure of seawater, reducing energy consumption for wastewater reuse. However, despite the benefit in terms of energy savings, several problems may occur in realizing this technology. The public perception of the use of treated wastewater in the mainstream water supply is a major concern. In addition, the FOR hybrid process requires desalination plant and wastewater treatment plant to coexist at the same site. Furthermore, large amount of wastewater is required to dry the FO process as shown in this diagram. For instance, to reach 50% dilution, theoretical energy decrease of approximately 0.63 kilowatt-hour per cubic meter of water produced, the amount of wastewater feed should be approximately twice that of the seawater feed stream. So it requires a large amount of wastewater. Lastly, the additional capital and operating cost for the FO process should be considered. Recently, new process to utilize draw solution with lower concentration than the feed stream has been developed to reduce applied pressure. This process can reduce the relative osmotic pressure difference between seawater feed stream and draw solution stream by situating these solutions, seawater and low concentrated draw solution, on the either side of semi-permeable membrane. This process is called draw solution assisted reverse osmosis (DSARO) process. In first outer stage, seawater is dissolved and fresh water is permeated into draw solution side. So seawater desalination is achieved at this moment. In the second outer stage, pure water is produced from the diluted draw solution. This new process has been identified as an energy efficient, high recovery process for the treatment of water with high salinity, although this configuration is still under development and no suitable membrane for DSARO has been developed. Lastly, reducing and recovering osmotic energy. The fourth step
Professor Hong, are you with us?
diagram address the matter of disposal and extract energy by using the concentrate. PRO, pressure retarded osmosis, generate energy by utilizing the salinity gradient. As a result of the process, the original high saline solution is diluted, and its osmotic energy is converted to hydraulic energy, which can generate electricity when used in hydroturbine. Osmotic energy can be also harvested by RED, reverse electrodialysis, which adopts selective ion exchanger membrane to control ion permeation. RED exhibits a higher power density than PRO for seawater and river water, whereas the power generation of RED is less for the high saline water and river water pair. However, the amount of energy produced with seawater and river water pair is still low for practical application. The application of PRO in practice is still challenging because PRO utilizes low saline water. SWR plants should be located where a sufficient amount of low saline water can be supplied, as shown in this diagram. The feasibility of osmotic energy recovery is not high enough to realize commercialization at present. However, potential for the osmotic energy recovery process is still good considering the extent of possible reduction in practical operations. If factors affecting this maximum extractable energy reduction can be improved, the amount of net energy generation will increase beyond the point of economic feasibility. This is a concluding remark. The maximum available margin and actual achievable energy reduction and the SCC of SWRO in each improving technical option that we have discussed in the presentation as shown in this slide. Based on this analysis, primary conclusions are summarized as follows. Minimizing irreversibility is effective, but operating issues are challenging. Decreasing osmotic pressure can be effective only with additional low saline water. Recovering osmotic energy may be effective but needs to be further developed technologically. We are still running really hard to further reduce energy use in SWR desalination to reach theoretical minimum energy consumption for seawater desalination. So we're still working really hard every day. Thank you for your attention and participation in my presentation. Be healthy and strong against the COVID-19. Also, see you all in person in the World Cup 2022 in Qatar. Thank you very much.
Thank you, Professor Hong. Thank you so much. We look forward to see you next year, actually, around this time. One year from yesterday.
Exactly, that's why I have the final slide like this.
Yeah, we look forward to. Oh, great! Yeah, and it seems that Korea will be able to make it. So hopefully we can see you next year, inshallah. Thank you. This is very informative, very good talk. Audience, please, if you have any question, please raise your hand or just write it in the chat. We have plenty of time here, actually. We have about 10 minutes for questions to Professor Hong.
Can I ask a question?
Yes, go ahead.
Professor Hong, it's a really nice talk and good to see you. So
Sophia.
I have a very simple question. So during your presentation, I mean, you cover wide spectrum of this desalination, covering this the different configuration and the trio. So one of your slides, I think the second part of your talk, you mentioned about the very efficient the LG tech membrane, and which have a very high the flux, right? I mean, is this still traditional the TFC membrane or something? Is a different different material? Do you know the material of the cell?
Yes, LG Chem actually purchased Nano H2O company, and the first generation is more like a, I would say, nano H2O membrane. But the second generation, Gen 2, as you see from this table, they add new coating technology. So basis is a polyamide membrane. But however, they have some new coating technique applied to synthesize this membrane. So now the rejection with a high permeability. I cannot say,
It's a nano membrane.
I mean, I cannot say exact, the chemistry of this membrane. And but however, yes, this basis is a polyamide, and but however, different coating and then different structure. That's all I can say at this moment. Okay.
Right. And also, I mean, in the later part of your talk, also you mentioned the new the configuration called the DSARO.
Okay.
Yeah, it's interesting, but so I think you also mentioned that still, of course, we need to develop new this module, the system. We need a membrane which can work with this our hypothesis and also our idea. So what do you think? What kind of membrane can be the idea for your DSARO system?
FO membrane, we need to reduce S factors. When you're doing that, you have some problem with the integrity. And DSARO process requires for the osmosis membrane with higher integrity. So it is very difficult to make such membrane. The S factor should be very small so that you're gonna have the better performance in terms in the water production. But at the same time, because you're applying pressure, this FO membrane or PR membrane, whatever you're gonna say, this the membrane should have certain integrity. So that's why I said the membrane which can be suitable or ideal for DSARO has not been really developed, in my opinion. Also very difficult to develop.
All right, so look forward to the learn more your new system developed in the future then.
Correct.
All right, yeah, thank you.
Thank you for your questions.
Yeah, any more questions from the audience?
Joy, he asked in the chat a question.
Oh, okay.
Yeah,
so I can read it, Professor Hong. So do you think this is from Joel? He is from ConocoPhillips, Qatar. He will give a talk later. Do you think that he's asking, do you think BRO could reach commercial stage in the next 10 years?
Oh, that's a good questions. I hope so. Yes, I hope so. I mean, PRO membrane is, in my opinion, is easier to make compared to F4. But at the same time, I mentioned in my presentation, it requires a large amount of, the additional water stream. That is very difficult to achieve. I mean, difficult to get. And that's why, technologically, yes, I think the PRO process can be commercialized, but I don't know whether or not this will become mainstream of seawater desalination because it requires large amount of additional additional low salinity stream normally can be obtained from wastewater treatment plant. So co-location of wastewater treatment plant and seawater desalination plants, that is required for commercialization of this technology.
Thank you.
So
Thank you. Good feedback. Thank you.
Your question.
Yeah, thank you, Joel. So there is another question, Professor Hong, from Jassim Ibrahim. So can the specific ionic composition of the water affect the SEC or the nature of the membrane or configuration?
Oh, I see. Specific. I mean, theoretically, the salinity, I mean, the osmotic power, osmotic energy of the solution will have significant impact on SEC. So yes, I mean, if you have more divalent ions, then that causes more, osmotic energy or most osmotic gradient across the membrane. So that's why I would say yes, solution composition is also affecting SEC. And the practical standpoint of view, if you have large amount of divalent ions, like divalent cations or anions, then it's going to affect operation of auto process due to scaling potential. So that's gonna cause some problem with the fouling issue, which means eventually it's gonna have some kind of some impact on SEC energy consumption. So I can say in two ways, operational and theoretical.
Yes, thank you. Any more questions from the audience, please? Dr. Shane, please go ahead.
Yes, thank you very much, Professor Ho. Your presentation is very impressive.
Thank you very much.
Especially with the audience, I believe. Yeah, nice meeting you. Yeah. So actually, Qatar has two big SWR plants in Umhalu area and Abu Pontas. They has a lot of the water production capacity. So anyway, the Qatar select to apply SWR process, sometimes hybridized with MSF to utilize all power plant facility. Anyway, our Karama is Qatar water energy sector set to the boron removal efficiency of 0.5 ppm. I believe it's very very hard regulation to control the boron in seawater, even in the out of product water compared to other GCC country. I believe that set to 1 ppm like UAE. So my question is, you already demonstrate, install and demonstrate the good facility of a pilot plant. You say not pilot plant, actual plant. So and yeah, in the second pass arrow, yeah, we applied the second pass arrow to maximize the removal of boron. But you assist the process, replace the second pass arrow with the MCDI. So we are very interested how much your plant can remove the boron up to a certain level. So would you give us a good comment?
I can say two things. Number one, the LG Chem membrane, I mean the outer membrane that we developed in our project by LG Chem, it is also high boron rejection membrane, 95%. So I would say if feed boron concentration is 5 ppm, then 0.5 barely we can meet that the requirement just by having the outer membrane maybe single stage. But the if we cannot meet that 0.5 the ppm requirements, then yes, we can use CDI or even BWRO. And however, CDI, I think Dr. Professor Son will talk about this, bromide or the this issue rejection issue more properly. But yes, by having CDI, we also can reduce further the boron concentration. So I say, with a newly developed outer membrane, as long as the feed concentration, boron concentration is less than 5 ppm, we should be able to meet that requirement. If boron concentration in feed water is higher than 5 ppm, then yes, we need to have additional treatment process like a BWRO or CDI. But from what I see from CDI performance, I think the CDI can reduce the boron further and below the concentration limit, like a 0.5 ppm.
Thank you very much. So I have one more question. So in the last section, you mentioned the energy consumption of RO, PRO case, and also I'm interested in RED because, as you know, all the GCC country industry produce a lot of the different types of water. Even they use the RO process to treat their own processed water. So anyway, the all kind of industry, release different salinity level water streams. So also I believe the RED sometimes is more practical or is good for energy, generation in Qatari case rather than PRO. This is my opinion. So how do you think in the future, what process, RED or PRO will reach the good level in commercialization step?
Okay, if you know this answer, just let me know. We're still in the process of evaluating which one is better, depending on salinity and depending on the amount of water used for this process. So I just avoid my answer for that question because there are so many uncertainty at this moment. I would say PRO, but there are many studies that have different opinion about that one. So
okay, yeah.
Okay.
I have a last question. It's okay, Dr. Mohammed Hassan?
Yes, we still have time.
I'm
Mr. Shane, go
interested
ahead.
in
I have plenty of time. So I love to have questions. So.
I like your project. So your treatment process targeting, I believe, some algae. Gulf also experienced one time, early 2000, the algae bloom. So also we have the water security when we experience the oil spilling. So how? I want to hear your opinion. So your the plant can depending well the oil spill disaster like the situation.
To be honest with you, we haven't really tested any possibility of oil spill in seawater with our developed technology. So I cannot say whether or not MTF mesh tube filter can actually respond to this oil spill crisis well or not. And that's the reason why the DAF is installed in typical SWR plants, even though we haven't really experienced algal bloom lately. So I don't know. Mesh tube filter, we haven't tested the oil issue yet. So I cannot answer for something that I don't know with the mesh tube.
Okay, thank you very much, Professor Hong.
Thank you, Dr. Shane. Professor Sean, go ahead,
Yes,
please.
thank you, Professor Hong, for the wonderful presentation. Yes, this is always very inspiring.
There are many questions concerning CDI.
Yes, you're right. CDI, I will cover the Q&A session. So my question is about, we have a very important breakthrough of desalination. So first one is the RO membrane using polyamide thin film composite. Second breakthrough is the ERD, energy recovery device. And then now it's time to make another breakthrough, third generation of desalination. So people look at the RO brine, which is the more about resource recovery, like lithium or some of the valuable materials. So yeah, you cover a lot of low energy, low carbon desalination. So in the third breakthrough of the desalination, in your opinion, many people believe this brine, the resource recovery, will be the next target for our seawater desalination to make a more value out of it. So, what's your opinion? What's our next most important research and then possible commercialization? Yeah, except your wonderful presentation. What's the target we have to see more future of the desalination?
I mean, the title of my presentation is low energy, low carbon, and out of brine valorizations. So I concur with your comments. Third, the wave of new seawater desalination is concerning the out of brine valorizations. I don't know whether or not this can be commercialized quickly enough to make significant impact on our SWR practice in next 10 years. I mean, this diagram is taken from my experience with SWCC, DTRI, as I mentioned in my presentations. They are developing, technology that can add value to our brine. For example, we can produce NaOH if we can concentrate our brine, I mean the NaCl solution, all the way up to maybe 220,000 or 250,000 ppm. And that is not really easy to do. I mean, you have to have a high purity, which means you have to take out all divalent ions from NaCl solution, and then you need to concentrate this one all the way up to 220 or 250,000 ppm by using various techniques. I mean, right now, ultra high pressure RO membrane has been developed, but as far as I know, I guess 120 bar or even 150 bar is the maximum pressure that we can apply to this, ultra high pressure RO membrane process. We still need to have like 200 bar, hydraulic pressure to overcome the osmotic pressure of these highly concentrated NaCl solutions. So today's, we talking about, I mean, this conference is for materials. So we need to have certain material which can withstand this ultra high pressure, like a 200 bar, more than 200 bar. And if we don't have some breakthrough regarding, ultra high pressure membrane or, the FO membrane, we may not be able to achieve this, out of brine polarization in commercial sectors. And that is my opinion. And also, here's another thing, NF membrane. If you try to use NF membrane as a pre-treatment in this process, then what we need to have is complete removal of divalent ions and complete passage of monovalent ions. I don't see such NF membranes available in the market right now. So we need to have the membranes NF or RO membrane, which can achieve the role of each process in this RO brine valorization process. So that's why we are here to talk about materials. Do I answer your question?
Yes, absolutely. You answer because the answer is nothing. You cannot answer this one. If you answer this one, you would have been very great in your effort for the desalination. Yeah, but it's very much reasonable to have a high pressure RO 200 bar. That could be next target. Also, we can see the more opportunity because now desalination is very established. So we need to look at another breakthrough to have a more energy efficient, also effective way of the desalting process, so that that's our generation. We can try to drive another impact of the desalination plant in the next couple of decades, right?
That's right.
Yeah.
I agree with you. Thanks, Professor.
Yeah.
Thank you for your questions.
Yeah. Any more questions? So if no more questions, I got one actually, Professor Hong. We are really happy to have you with us. You are one of the world pioneers in the field of desalination. It's a very good chance, very good opportunity. So for the DSA RO membranes, you mentioned about the integrity. This is like mechanical integrity, chemical integrity. What kind of integrity you are?
I would say mechanical integrity is the first thing that we need to look at, and also chemical integrity. Yes, I mean depending on application, chemical integrity is also important. But I mentioned about pressure applied to this process, so you have to have integrity as well as the transport. I mean see, I mentioned about S factors. So in order to have higher permeations, you have to reduce S factor. But by doing so, you're going to lose mechanical integrity, stability. And so that's what I mentioned, the integrity issues.
Yeah, perfect. Also, another thing on the LG Chem, the new membrane that developed the polyamide one. So what is the lifetime of this one, Professor? Especially under the especially as the high temperature of.
This one is just on the market, and then I'm not a representative of LG Chem, so I cannot mention this one. Okay. And as far as I know, they tested this one in the Middle East for several pilot plants, and as far as I know, they are doing pretty good. But like what I said, this one is just on the market, and then we are also testing in progress. So I can tell you the lifetime or lifespan of this membrane maybe next year.
Yeah, we look forward to that actually. We look forward to that, and we look forward to see you as well in person next year in the World Cup. Thank you, Professor. We're really honored to have you with us. Yeah, we're really honored. Yeah, thank you, Professor. Thank you so much. So now we will move on